Hi, everyone, and welcome to the MIT Robotics Seminar. It's a pleasure to introduce today's speaker, Professor Gaurav Sukhatme. Gaurav is Professor of Computer Science and Electrical and Computer Engineering at the University of Southern California, and he's also an Amazon Scholar. He's the director of the USC School of Advanced Computing and the Executive Vice Dean of the USC Viterbi School of Engineering. And he was a chairman of the USC's Computer Science Department, from 2012 to 2017. So Gaurav got also his PhD from USC, and his research interests, as you're going to see today, are spanning networked robotics, learning for robotics, as well as field robotics. We're actually coming out of a week in which we spend a lot of time together doing field robotics. At least the students are doing that, I guess. So Gaurav got plenty of recognition for his work. He's a fellow of AAAI, AAAS, IEEE. He's the recipient of an NSF Career Award, the Okawa Foundation Research Award, as well as an Amazon Research Award. Few more cool things. Gaurav is actually one of the founders of the Robotics Science and System Conference, the RSS Conference. Was the program chair of ICRA in 2008, IROS in 2011, and he's going to go back and host RSS next year at USC. So RSS 2025 is going to be at USC again. So thanks for hosting it. So finally, he's the editor-in-chief of Autonomous Robots. Gaurav, thanks for joining us. Thank you so much.
All right. So thanks so much, Luca, for inviting me out, and thank you all for coming. And so I want to talk to you today about a sort of a line of work in our lab that has to do with seeing how far you can push end-to-end reinforcement learning for a class of multi-robot problems that people already know how to solve. And so the idea is, can you get interesting behavior out of end-to-end RL for a fairly well-understood multi-robot multi-robot coordination problem? And that's the exploration we embarked on a few years ago, and so I want to tell you a little bit about that. And so this talk will be all on one platform, and so this is a highly resource-constrained platform. Several of you probably have flown it, and you know it well. This is the Crazy Fly. It's easy to buy, easy to fly. It's tiny. The amount of space you have to play with is measured in kilobytes. And of course, there's no GPU or anything like that, right? It's typically run a single thread of control. The one nice thing is it has a fairly nice IMU on board, right? So you can do things at fairly high frequency, provided your control loop doesn't have too many things that you want to do in it, right? OK, so this is the platform. And so, many years ago, 7, 8 years ago, in collaboration with Nora Ayanian's group, my group and I were quite active in doing trajectory planning for swarms of quadrotors. So we would work on problems of this type, right? So there is a group of these. There's 50 odd of them. They're somewhere in space. There's some set of obstacles they have to navigate through, and they're supposed to end up at some desired end locations. This is a well-specified problem. And this instance of the problem we were working on was where, at planning time, before you do this, you know where the obstacles are. And so the question is, can you quickly generate a plan that causes these robots to go in some efficient way from start to goal, not hit the environment, not hit each other? And the quickly is because ultimately the vision is, if the environment changes and you can get an updated map quickly enough, then you can replan, right? Hence the quickly. And so we had a series of papers on how you do this in ways that account for downwash when one robot is above another because it throws the robots off, and how you do this in ways that are efficient as an instance of a multi-agent pathfinding problem. And broadly speaking, you plan on a graph, and then you do some smoothing using a couple of tricks that we had published at the time. So we sort of knew how to do this, but there's obvious issues with this, which is, it's a setup designed to plan based on knowing what the environment looks like. That's the fundamental premise, right? And whether you do that fast and you do it over and over again, or whether the environment changes slowly and you don't need to do it frequently, but the fact is the pipeline very much is build a representation of the environment and then plan on the representation and then act, right? And this is a paradigm that we all know how to do. We've done it for many years. And it's remarkably good, right? It scales well. With modern solvers, you can really do this for large numbers of robots, et cetera, et cetera, et cetera. But the question that I had in my mind right around 2020 was, could you do this by sort of abandoning this paradigm? Could you actually say, you start at some known locations in an environment, you command vehicles to go to some location in the environment, and they just do it irrespective of what appears in their way. I don't say do it efficiently or provably correctly or even provably safely, but can you at least do it to the point where you start to feel that empirically there's something there, right? So it's a slightly different goal. It's not quite exactly the same problem, but it's close to the original problem that I sketched. And I didn't know anything about end-to-end RL, and so this was my little foray into trying to learn whether a problem I understood well, at least a slightly relaxed version of that problem, could be solved using end-to-end RL. The problem is also different subtly in other ways, because in the planning setting, the assumption is there's a low-level flight controller that already exists, and you reason at the level of waypoints. Whereas in this setting, we're going to assume that there is no such controller. And so we're going to learn to fly, and we're going to learn to navigate from A to B, and we're going to learn not to hit stuff along the way. Right? So it's almost the same problem, right? And so the usual, as is usual in talks like this, the answer is yes, you can do this. And there are videos that suggest that you can do it, right? And so these will appear at the end of the talk. So now, so this is the question, right? There's a further constraint we had in mind is, can you do this? And also, can you do this with no physical demonstrations? So in other words, the data for training this system cannot appear from flying the vehicle around. So that's an additional constraint. It's a self-imposed constraint. It need not exist in all of robotics, but it's kind of a neat constraint to have because as the subsequent years have shown, it's becoming quite important in many settings to really worry about where the data come from, right? So those are the constraints. The other thing is we were pretty sure that we wanted to do this for real, not on an abstraction of the vehicle you want to fly, but by directly generating thrusts. So each vehicle has 4 rotors, and you actually want to control how fast the rotors move, right? Not like a point which you move around in space, and then there's some lower level decomposition that converts that to thrusts. The attraction was A, to see whether this can be done, and B, to see whether the maneuvers you get out of this, if successful, are in some way different than the maneuvers one may program, or that might emerge as a result of layering a planning system on top of a low-level controller that you understand. Right? And so that was sort of the other attraction. So our first cut at this was to forget about multiple robots and just learn how to fly a single quadrotor. And we learned how to fly a family of these X configuration quadrotors of different moments of inertia and different masses and so on and so forth. And it turns out simply by doing fairly vanilla reinforcement learning and extensive domain randomization, we're able to do very good attitude stabilization and trajectory tracking. So there's no navigation happening here. The vehicle is just asked to sit at a particular location. You disturb it wildly, and it regains that position. This is all happening in Vicon, by the way. Right? Subsequently, we have shown how to do this without Vicon and so on, but these experiments were in Vicon, right? And so there are no obstacles here. This is a single robot only. There's no navigation here. But you can learn flight fairly well, and you can learn it completely offline in simulation. And I'll show you a little bit in a second exactly what the details of that are. So this was our building block. And so the question is now, can you do the more general question that I'm interested in here, which is, can you do coordinated flight, and can you avoid hitting obstacles and so on? So what I'll tell you today is how to do this, and some properties of the learned network, how much we think it generalizes, how we've stress tested it, and some of the insights from it. And if you're interested, there's a Coral paper from 2 years ago that describes it, and then there's a subsequent ICRA paper that I'll tell you about later that does it. Right? So our view of the world is textbook, and I mean that literally. So each robot just sees the other robots and the obstacles as part of the environment. There's nothing fancy going on. Each robot commands 4 actions, which are the speeds of the 4 propellers it controls. Stuff happens in the environment, and the agent gets some reward back. I'll tell you a little bit about what the state is, and then we close the loop in the conventional way we do this. So the state is composed of a bunch of stuff. Each quadrotor measures the relative position between itself and the goal that it has been told to go to. The assumption is that everything is happening in a known coordinate system that they all are registered to. Each quadrotor has access to its own velocity. It has access to its own rotation matrix, so it knows its instantaneous roll, pitch, and yaw. It also has access to its own angular velocity, and most interestingly, it has access to the relative position and the relative velocity between itself and its k closest neighbors. Right? This number k is going to be important. If k is on the order of the size of the entire system, then you've built a fundamentally uninteresting system in many ways. If k is small and the overall size of the system grows, then you recover the property that people in multi-robot systems have known for a long time, meaning that for tasks like navigation and obstacle avoidance, you don't need to know what somebody in London is doing. You should be able to navigate to the goal without caring about their state. So this is if that property didn't hold, something would be fundamentally wrong. And but picking k is an interesting exercise in itself, and we'll return to it in a little bit, right? So this is the world. Basically, each vehicle sees a neighborhood of k. The interesting thing, of course, is who's in your neighborhood changes very rapidly. And so there is an implicit assumption that there's some underlying technology that allows you to range to vehicles near you and pick out the ones that are, so you can perform an ordering operation on range. And as long as that ordering operation separates your k neighbors from the others in a reliable way, in both position and velocity, you're okay. And so that is something that is less doable in some settings and more okay in others. And each robot generates 4 numbers, basically, as the actions. Right? We do normalize these actions. Each vehicle is a little different from another. And so we have sort of a crude way of simply categorizing max torque and min torque to the 0-1 range. This is on a model that is just some fit to the 10 or 15 vehicles we play with, and then we just forget about it. So it's not particularly good for one vehicle or another, right? It's not over-specialized, it's not learned, right? So it's something that we just do to make things easier for us. So we need some sort of a simulator to train in, because we set ourselves the goal of training entirely offline with no real data, right? So we have to somehow generate actions, we have to somehow generate new states from actions, so we need a simulator. And so we have a textbook model of the dynamics of these vehicles, right? So this is about the sort of the simplest possible thing you can do to simulate one of these, right? So easy to implement. We have a little custom simulator that we wrote that makes it go super fast, right? But the really interesting thing is at the bottom. We have a simple randomized collision model in this simulator. So I'm going to tell you a little bit about what it means, what we do, and then we'll return to it later in the talk, because I think it's super important how you do this. So when 2 vehicles collide in our system, we set their speeds in opposing directions of a plane along which they collide to essentially 2 random vectors. So you come in, we don't apply any kind of conservation law. We pick 2 velocity vectors, which only are not guaranteed to lie in the same half plane. So they're sort of opposite to each other, right? But we pick that randomly, and there's a uniform random distribution over the direction. And the speeds are picked between 0 and the max possible speed at which these things fly, right? So this is not a physically realistic model. This is not what happens when even 2 balls collide. It's not an idealized collision model. It is a simple model of a thing that in cartoon form looks like a collision model. It's super important to realize this, right? It is not a 0th order model, or maybe it's a 0th order model of the physics, but it is not even a 1st order model of the physics. It's somehow less than that. It has one key property. It's fast, and it causes vehicles to stay in play after they collide. And that's the key property that you need, because if you have any hope of recovering from collision, you have to be in post-collision states in the training regime. One of the problems with doing models that don't cause you to see weird states after colliding is that you don't know what to do in those states. So this thing, for which I have no equations, is how we do it. Right? So it's a sort of odd way of generating data from the simulator. Right? So on the one hand, the top is well understood physics, and then layered on this is a little bit of a kludge. Okay? But it has some interesting properties. It's not, you can do many things, but we think that this is sort of the right thing to do. Right? And then you need a set of training environments, because in simulation you need to basically start in some state, generate some actions, and you need to explore. And so the way we do this is we generate a set of geometric shapes that we want these robots to fly to. And so the red robot is supposed to go to the red target, and the blue robot is supposed to go to the blue target. And you arrange these targets in certain geometries, and then you move these geometries around. And in the simulation, you basically swap through a bunch of these scenarios. And over time, you hope, if you converge, I haven't shown you the reward structure yet, I will in a second, that you will converge to a state where these things will fly to the goals. Right? That's sort of the idea. And there's a bunch of these. They're picked to sort of be illustrative of the kinds of things we ultimately want to do, but they're not particularly significant in and of themselves. Okay? And so the last thing I need to tell you a little bit is what is the reward design, and it's not particularly unexpected, right? So obviously you need some reward for relative positions to the goal. You want things to fly towards the goal, right? There is a fairly significant penalty for colliding, but equally well, there is a term that actually basically penalizes for being very close and entering into this sort of pre-collision state, right? So you don't want just this delayed reward when you collide. You also want some sort of negative reward as you get too close to each other, and you need both these things. So you definitely don't want to collide, and the simulator will try and expose the system to post-collision states so that when you do collide, you may in fact have some sensible actions that you've learned. But all that being said, you also want a fairly steep penalty in states leading up to collision. I'll tell you a little bit at the end about how you play with these states in a replay buffer, and you make the system see them more frequently than other states and so on. So there are some other tricks that go into it. And then this last thing is just the thing that causes you to hover in place. And this is, in fact, what I showed you in the previous video. So when I said we could do a stable hover with a single quadrotor, all you're doing is basically saying sit in hover about a set point, right? So that's just inherited from this single vehicle. So this part is how you learn to hover. The first term is how you learn how you get rewarded for flying to a goal, and the two terms in the middle are the penalty for collision. Right? That's the reward function. Yeah?
Is the last term, the very, very last term, yaw?
It is not, hold on. It is yaw. We don't, because they're symmetric about yaw. But that being said, they're not perfectly symmetric about yaw. So even for vehicles like this in hover, we want a system which doesn't believe that spinning round and round in place is a reasonable good state, and hence the penalty.
Wouldn't that be omega? Spinning would be omega.
So the angular velocity, so you don't want the yaw to change, but you also don't want it to change fast. So you want to penalize the velocity and the position. So you sort of want to hold a stable direction, and you don't want to turn. Now, in principle, you're right? You could only penalize the velocity, and it should all work out. But it helps. Yeah. And what we do is basically just maximize the expectation of the discounted reward, and that's basically it, right? So this is we just run a simple variant of PPO to basically see if we can learn a policy that is performant for this task. Now, there are a couple of things we test out, which I want to tell you a little bit in detail. So one of the things I want to tell you about is, so now what does the system actually look like? So there are basically two encoders at the input. The observations from the vehicle's own state go into a small network that code them into a latent. And the observations from the neighbors basically go into another encoder that code those. And one of the things we want to do is we want to reshape that to get k pairs of neighbor observations. And we perform a mean operation on them because we, in this setup, this is sort of the so-called deep set setup, we don't care about one neighbor being more important than the other. So we want some permutation invariant representation of all k of your neighbors. Subsequently, I'll show you that in fact, it helps to know some neighbors. It helps to attend to some neighbors better than others, and I'll show you that as well. But this is sort of one where all you do is capture your k neighbors, and you don't really care for one being more important than the other. And then at the output, there is just a simple decoder. And all the networks are small MLPs, basically. Okay. So that's one architecture. And the problem is that it's nice to sort of, it's fast, and it's easy to train, and it's nice to capture just your neighborhood set, but it doesn't capture this business of the blue robot flying fast towards the green robot, yet being at the same distance that the red robot is from the green robot. And so sometimes, two things being near you, but if one of them is hurtling at you at high speed, you want to attend to it more. So you need some mechanism to actually differentiate between things, even if they are in your k set. And so our technique for this is just to add a small attention layer to the system. And so what we do here is these self-observations stay the same, but the k latent vectors for the k pairs of neighbors are subjected to k attention scores that are learned over time. And therefore, you pay attention to the k that matter more, and so the training takes a little bit more longer, but it's actually far more stable, and you get better results as a result of this. So you cut at k, where k is a hyperparameter, and you learn to attend to them differentially, as opposed to all the same. So if you do this, it's kind of interesting to see what the models actually do. So there are three pictures here. There's, on the x-axis of each graph this is all training. So this is just steps of simulation. So we trained to up to about 1 billion steps. On the y-axis is, in the middle one is the average distance to the target. On the extreme left one is the total reward. And on the one on the extreme right is how long the robots actually stay in the air, the fraction of time for each episode that the robots stay in the air. Right? So ideally, you want, on the right, them to stay in the air all the time and kind of not crash and burn. On the left, you want a strategy, hopefully, that gathers a lot of reward. And you want the average distance to target to really go to 0, insofar as it's possible. If there are two robots trying to fly to the same target, they'll never quite end up at 0, but within the realm of what's possible. Right? And there are 4 things being plotted here. So there's a system where the robots are not aware of their neighbors. This is sort of the blind system, which is just the straw man to compare against. There's a single MLP that we use just to convert actions into outputs. And then there's this deep sets technique and the attention technique. The blind system is obviously not as good, so that's not so important. But if you look at the others, it's a little hard to tell that they're different. I mean, they're a little different, but there's not much to separate. So if you look at the average distance to target, and you look at the deep set setup versus the attention setup, they seem to navigate robots to targets pretty well by the end of the 1 billion or so training runs, right? And they seem to gather roughly the same reward. But that's not actually quite right, because if you look at it a little more carefully, again, training on the x-axis. But now if you look, for example, at certain more challenging tasks, if you look, for example, at the middle panel, which is the average number of collisions for a pursuit evasion task, or on the rightmost one, where you look at the average number of collisions where all robots are being commanded to fly to the same goal, in other words, you're trying to force them to collide with each other, then you can see that the attention-based technique is a little bit better. You can sort of tease them apart. So if you average over a wide general set of tasks and they're not too cluttered and so on, it doesn't matter. But when you want to crowd them into small spaces, attending to the ones that are close to you that will cause you to collide does matter. So that mechanism is not overkill. It actually does help. And actually, we looked at the attention weights. So if you look at the attention weights, you can see that from the point of view, for example, of the blue vehicle here, you can see that, that the relative importance of red is greater than gray, given how they're flying towards each other. And the relative importance of gray is greater than green. So you can actually see it in the network weights quite nicely. So the representation learned is actually meaningful in this setup. Now the question is, what can you do with this? So you go off and train. You do this. I haven't yet shown you this flying on real robots. I will soon. But what happens if you walk in and say, well, you trained with 10 robots, but I decided to have 20? So it's a natural question to ask. And so the question is, can you just take the network you learn, and since it runs on each robot, can you just deploy it when there are 20, and does the thing still work? Our setting, by the way, is a bounded volume. And so that's why this sort of makes sense to ask a question like this. Right? And so there's an interesting thing that happens here. So on the x-axis, I will just increase the number of robots. And on the y-axis, I have this measure, which is the number of collisions divided by how long the episode lasts and how many robots there are. Right? So I somehow want to normalize for these things. Right? Because obviously, if I have a bounded volume and I put 100 robots in there and they're all flying around, the probability of colliding is higher. So I want to normalize for the number of robots, and I also want to normalize for how long the episode lasts. You can get away with very few collisions if you just run the thing for 1 second and declare success. So we don't want to do that, right? So I'm going to count how many times they collide, normalized by these two things on the y-axis. And so the question is, how does this number grow as you squeeze more and more robots into that same bounded volume? And that's what this picture is trying to capture. And the question is, if you just deploy the system you learn, what happens? And that's the one which is labeled pre-trained here. And so pre-trained simply means we are learning in a system where there are 8 robots, and k is 6. So it's a pretty high value of k, considering that the whole system has 8 robots, and you learn with 6, which means there's only one thing that doesn't act as your neighbor. So obviously, it's not very useful if you learn this 8-6 behavior, and then that's all you can do. First of all, 6 is very generous. And secondly, if it doesn't work on anything else, well, then it's really kind of annoying. So the 8-6 system does really well in the bottom left. And if I just deploy it on a system where there are 16 robots, and I don't do anything else, I just deploy it on the configuration to run as though the world is 16-6, then it works pretty well too. I mean, the number of collisions goes up slightly. But if I deploy it on 32 robots, and I don't change anything, well, things don't look so great. That's that dashed line that's growing, right? And so that's this point here. And then pretty much after that, it's hopeless, right? So you can't just take this pre-trained system and deploy it on 48 robots. It's essentially useless. The things just collide all the time, and you don't stay in the air very long, et cetera, right? OK. So you can do a couple of different things. The two obvious things to try are, one is to say, can you do some fine-tuning? So you have this system. Can you come in with a little more tuning? So you trained with 8-6, and now you want to do 32. Can you do a little bit in a simulation where you train with 32-6? But the number of steps in simulation you're allowed to take is not as large as the original number of steps. So you train for 1 billion steps. Can you add 20% more time or something like that, right? So that's what the solid line shows. And so with 200 million more steps of training in the new setup, you do a lot better. As you can see, that's the solid red line, right? So that's this line, this one here. It ultimately does break. Things don't work quite as well. Training from scratch as the system gets more and more complicated actually is harder, but it pays off at some point. And that's the other line. I'll come to you, Russ, in a second. So that's the obvious other line, which is just forget about all this, right? So tell me how many robots there are. I'll go off for a day. I'll just train for 1 million steps, and then 1 billion steps, and then I'll be fine. And that line actually is pretty good, right? But it really pays off only when the system gets very big. So there's a lot of value to fine-tuning up to a point, But fine-tuning has limits as the gap between the system you care about and the gap the system you trained on is different. Yeah.
I'm just curious if you have only 10 meters and 64 robots or 128 robots
Yeah.
and a random collision model.
Yeah.
I wonder if you're going to get pinball effects.
Yeah. You get exactly that. You get exactly that. You get cascades. And that's not anywhere, like there's nothing that looks forward in time that tries to somehow do something different. We didn't change so like ideally what you want to do is as it gets denser and denser, you want to actually more sharply penalize the pre-collision states. And you may actually get better. We're pretending that the world is the same at 128 robots in the same volume as it was with 6 robots. It's not clear that you want to learn the same behavior, actually. So yeah, you're right. That's exactly what you get. You get things bonking off each other, and then just, yeah.
Now, pre-trained and fine-tuning is better than scratch. Is that because of the extra, it's like 1.2 thing?
That's it. Yeah. So you get 200 million more steps of seeing it, and you get some mileage out of that. It's not entirely without use. You get some mileage out of it, but it's not forever. So you can't sort of come in and say, I have a drastically different system. All I need is a little bit more fine-tuning. At some point, training from scratch it does take over. Yeah. Yeah. It's a little bit of a contrived task, right? Like it's not super important. Like, what does it really mean to squeeze thousands of robots into a room like this? Like, there's no particular reason to. This is a little bit of a stress test to see how, when you separate the thing you trained on from the thing you care about, how does the system behave? This is mostly that, right? It's not really that somehow squeezing more robots into a bounded volume is intrinsically interesting. But it gives you a nice control experiment, right? Right, I already said all this. Okay. And so, the kinds of behaviors you get look pretty in simulation. You can tell robots to fly to goals. You can move the goals around. The robots fly to the new goals. You can do things like tell the robots to fly in kind of a setting where the goals are moving around, and the robots will do the right thing. These are all simulated results, and they look pretty good, right? You can do crazy things like tell 32 vehicles to fly to the same goal, and then you get behavior like this, which sometimes people then use fancy words for it. They call it emergent behavior and things like that, which is fine, whatever. I mean, it's nice, but let's not. I'm not keen on overdoing the interpretation for it. The interesting thing is that now what you can do is you can take. Actually, in this case, we're flying this deep sets technique because we ran out of space for doing the attention mechanism online. But you can do very small networks like this. So I forget exactly how many, I wrote how many network parameters there are, but I think this one has 30-odd neurons in the self-encoder and the neighbor encoders added up. And it's like 1,500 parameters, basically. These are fully connected MLPs, right? And we're running at about 100 hertz on the vehicles, and we're just basically telling these things to go in, some start goals to some end goals, and the system is running. This video is fully in Vicon. We now do this we resort to the Vicon a little bit less because we are actually following visual texture on the ground, so you can actually fly a fairly nice camera now on these things, but these are in Vicon. The other interesting thing about it is that you get interesting collision behavior. So occasionally they fly into each other, like then, and you get 2 or 3 collisions. They'll bounce off the ground, and they fly. Right? So if you do control barrier functions for safety, then this is death. This never happens. You can provably show that this is never meant to happen. And in any system where safety is critical, this is not tolerable behavior. But if your application is benign towards this sort of setting, then it's not an entirely unreasonable outcome. It's kind of something that this airframe can tolerate, so you can take advantage of that. And RL is good at taking advantages of these little things. This is where the collision model comes in handy. It turns out that something very complicated happens when these vehicles collide with each other. There's no way any of us is going to be able to accurately simulate that. But it turns out that for RL, you don't need to. You need to just about simulate enough so that some post-collision states are occasionally in the training, and you learn how to recover from them. So this is an interesting little artifact. For projects where, again, safety is critical, this is not an important thing, but it's an important thing to just observe that RL is good at some of these things. Right? We did some baseline comparisons, so we looked at standard ways of doing this. There are some nice ways of actually computing collision-free areas and planning. So we have compared against a few of their approaches. So like if you are allowed to pay attention to your neighbors, you can construct a Voronoi cell around you, and within the boundaries of that cell, you can move. And if you know the maximum speed at which everybody can move, you can move with abandon at max speed towards a boundary that takes you closest to your goal. And this method is well known and works really well. And in fact, it comes with guarantees. So it's a great method, right? And of course, it works. If you look on the left, we implemented a variation of max BVC implementation, and on the right is our learn controller. And they're doing the same thing. There are 4 robots on either end. They're in some start locations. They're told to swap their locations, sort of fly through each other. Qualitatively, you probably noticed that they fly a little differently. You can see that. You can see that in the sort of the results. You can see on the right, the lower panel is acceleration in both sides. The upper panel is velocity. You can see we fly very aggressively. So our stuff is on the right. The other ones are on the left. And there are 2 things to note. The learn controller flies a little bit aggressively, and also the learn controller obviously doesn't give a safety guarantee. Right? So it's important that the comparison is to be taken in that spirit, not A is better than B. Right? It's important to calibrate. You can also do things like weird things like throw objects in the midst of these things, and as long as you can track the object, it doesn't really matter. You get very fast reactive recovery from all kinds of disturbances. Now, admittedly, with fast online planning these days, you can do many of these things. It is not the case that building a representation of the environment and then reasoning and planning on it has gone away by any means, right? But these things are quite doable in this setting without going through that intermediate step. So the question is, everything I showed you so far, there's things flying around, but there are no obstacles. And so if you want to navigate from some start locations to some end locations, my first version of the problem had some obstacles, and ideally you build a map and you plan on the map. But as you discover obstacles along the way, will you fly around them and still fly towards goals? And yeah, I mean, this generalizes to the setup that we really care about, which is not only are there other moving vehicles in the environment, but there are also static obstacles in the environment that are unmapped, and you discover them as you fly, right? And in this case, what you have is ranging to the obstacles and to nearby neighbors. And I will sort of not go through all the details because the basic details are the same. There's a couple of different things. So our obstacle representation for the older work didn't use sign distance fields, so we use them now. And our attention module is a little bit different, so I just wanted to show you what it looks like now. So how we really do this now is that we have 3 encoders, 1 for the state of the vehicle itself, and 2 for the static obstacles and moving things in the environment. And then we have a multi-head attention module that tries to learn the attention weights for which static obstacles and which nearby robots get priority. So those 2 are learned in one fell swoop. And then there is a simple sort of latent representation that emerges, whose output is fed to a MLP that generates the 4 actions on each vehicle. And this is trained end to end again. With one change, which is we do this thing with a replay buffer that's actually quite useful, and it's a trick that many of you have probably used, which is what we want to do is we want some mechanism to amplify collision events, basically. And we want to sort of enhance collision aversion among robots. So what we do is we store in a buffer the states leading up to a collision, and we make sure that the robots in simulation see those states more frequently. And we discard them from the buffer when they've been seen a certain number of times, and that's a tunable threshold. And this mechanism helps a lot. So it's not like collision recovery is going to be the holy grail here. It might be an amusing artifact. You still want to generally bias the system towards things not running into each other, and this is a kind of well-known way of doing it. It works very well. I wouldn't go into the details of this, but these things all, it turns out they do matter. So you can take some of the components out from this, and you can take out, for example, this multi-headed attention module, and you can take out a few other things, and you can show that in fact they contribute in a meaningful way to the performance of the system. So they're significant. Yeah.
Before you introduced the obstacles, the network side was 1,600 weights and about 30 neurons. Now you got the
Yeah.
head attention, encoding,
1820. Yeah. So yeah. I didn't remember it off my head, so it goes up a little. Yeah. Yeah.
How are you actually doing the range?
Yeah, so now there's a small ranging module that is on the Crazy Flies, which is quite reliable, and we use it for the static obstacles. We have no way in practice of doing it for other vehicles. And so what we do for the other vehicles is we cheat. We expose the positions of all the vehicles to a centralized place, and we hide the relative measurements to the vehicles that don't matter from each vehicle, and only send those others corrupted by noise to each vehicle. So there is no range measurement, right? It turns out the range measurement is pretty bad because you can corrupt them at least very significantly. We also introduce dropouts where you occasionally just don't get range measurements. But yeah, there is not a good, for this small a vehicle, there is not a good ranging mechanism that in a full 3D sphere around it can do ranging. Yeah. So the measurements are contrived. They are physical measurements, but they're not from a ranging system. That's a good point. Yeah. Yeah.
This is the operating center. Like there's lights wrong with like different neurons or coefficient goals. But not as in the reverse structure that there's an adverse response that can be like a two-pair of mark of.
So there's no jamming in the sense that is somebody deliberately trying to sort of fly towards you. No, but like you saw me throw a beach ball into the system. You can do that. I mean, the system depends on ranging to the 6 things closest to you, right? That's it. That's an entirely myopic view, right? So somewhere there's a goal. I know my current state. Left to myself, I will fly to the goal is the behavior these things learn. Everything else is a disturbance. That's it. That's all that's happening. So there's no game theory. There's no adversaries. It's all. Well, there's no planning. It's just. Yeah, it's gradient descent, right? I mean, left to myself, I want to go there. And if I can't, then I will do whatever it takes to be rewarded as being perceived towards going there. And I will generate control actions that maximize that. And it turns out that those are performant. Yeah?
You get caught in local non-contact states.
Yeah, you can fly down an alley. We've absolutely tested where things fly down alleys. They have no notion of any, you don't build a representation, so you have no idea. So you will fly down an alley. But there's enough noise and exploration that occasionally things will, but can you get endlessly stuck? Yeah, you can get endlessly stuck. It can happen. So this is the biggest thing with these systems is they exhibit interesting behavior. They're curiously learnable. They explore parts of the state space that you wouldn't see otherwise. But they are not designed like this. They are not designed to provide guarantees. Now there are other things one can do, and we have some new work on changing that, and other people have done some work on that. But as described, they address one piece of the problem, but not some of the other pieces that you care about. Yeah. Yeah. And empirically, they do pretty well compared to learned control methods. They do pretty well compared to things like safety barrier certificates in terms of how well they do as measured by how goal achieving they are. So you can measure a system by how live it is. You want it to go from A to B. You measure how good is it at going from A to B. But of course, in the process, there's another axis, which is how often do you collide. And ideally, you want a system that never collides and is better than any other system at going from A to B. And with many of the guaranteed methods, they're not as live when the safety considerations are paramount. So if you have very high obstacle densities, for example. Whereas these systems will, if you have the luxury of bouncing off of an obstacle, well, I mean, your goal achieving behavior can be pretty good, right? So in dense settings, you get interesting behavior. But it's a slightly different version of the problem than somebody who's interested in safety might define. So take the comparison for what it is. Right? Yeah, I mean, I don't know if you can see what's happening in the small video on the left, but that's a top-down view. You fly in extremely dense obstacle fields. This is obviously in simulation where one can sort of get very, very nice results. There's lots of robots flying around with hardly any space. Things, of course, are a lot easier in the simulated setting. But they work pretty well. I mean, here's 8 vehicles flying around. The obstacles are much less dense here. This is a small network, right? Runs very fast on board. And small memory footprint, single-threaded control loop running pretty fast. We're not even using the IMU at all the frequency that we could use it at. And fairly stable and reasonably repeatable behavior. All our experiments are on the timescales of 2, 3, 4 minutes. These things are generally not, in terms of battery, are not really well suited to doing long-term experiments. So these are small episodic experiments. All right. Okay. So I'm not going to try and draw too many conclusions from this, but I am actually now more interested in how to systematically generate such small networks. Because this was a foray into which began as, can you do something interesting with end-to-end RL for this particular problem? The answer is yes. It's quite performant. What was more interesting to us that you could do it with very small networks. Maybe that shouldn't be interesting because after all, the lines of code you need to fly one of these vehicles is not a lot of lines of code. And so there is some fairly compact representation waiting to be learned. And maybe it's not a big surprise that you can learn it. But nevertheless, to me, it was surprising. I think how you simulate for such systems, and maybe for other robotic systems, is quite important. You need to simulate so you can simulate fast enough that you can actually I mean, this is a desktop machine doing 20 hours of training, and you can have a new controller up and ready, right? So if you change things, you can sort of make a change, and next day you can play with it on the real robot. So, and that's I mean, on real machines, it would go a lot faster. These were not particularly big machines, right? But you need to get the inductive bias right. So if you have a good inductive bias, you can learn sort of end-to-end useful things. And for the things you can't model, it's important not to over-idealize. It's important to model something about otherwise unmodelable phenomena. Abandoning them is no good, because then you don't learn to recover from states which you will inevitably see in a learned system. Yeah, if you we've tried, by the way, other ways of doing this. We've tried doing idealized collision models and so on. They do not work as well as the model I described, right? So that's an interesting sort of weird finding, right? It sits somewhere between having a crisp inductive bias whose structure you understand, you can write the equations, and it's good, and it's good for a reason we expected it to be good. And then the sort of middle ground, right? And so you can get some mileage out of RL. We spent no time on this project tinkering with our version of PPO. We spent no time on this project tinkering with any of the other machinery that one normally tinkers with when one writes learning papers. We did tinker with K. How many neighbors should you have? And in fact, we have a sweep that suggests that, and this is a known result, I think, that depending on exactly how you set things up, people seem to converge on 6, 7, or 8. And it's not super surprising if you sit at the center of a cube, there are 6 faces around you and 8 vertices around you. And after a while, it ceases to be important. So somewhere there is the right number. We picked 6 after doing a few sweeps. We have done it in physical robots with as few as 2 neighbors, and it still works quite well. It doesn't work well at high densities, obviously, so it's not independent of sort of the density of robots. So that's another thing. In fact, the physical experiments that I showed you were all with k equal to 2, because we couldn't afford paying attention to that many neighbors. So there's some interesting insights here. So, I really don't think you could probably read that, but if you can. So we have sort of a line of work in trajectory planning for vehicles like this, and I haven't completely lost my fascination for that line of work. We have a separate thread of work where we continue working on that. This work I described today was really end-to-end learning for a problem very much like the original video I showed you. We have a new line of work in how you systematically learn small control policies. And so if you have me back someday, I'll tell you about those. That is becoming kind of an interesting focus for our lab. So if you had a task that you could define well, could you, in fact, from a set of architectures, like assume you're doing this encoder-decoder structure with one latent representation, and everything is a fully connected MLP, can you actually tell me, if I give you, you have so many neurons to play with, can you tell me which is in some sense the best such network? And there's some work in hypernetworks that poses this question. We've adapted it to some interesting robotics problems, and we have now some papers on it. And we also have some interesting new work on potentially finding small policies concomitantly with finding the right network. So ideally what you want to do is you want to propagate the loss that you get back and use it to tune both the network topology and the policy that you're learning. And we have shown recently that it may be possible to do that. So we're pushing ahead on that. But I haven't lost my fascination for doing for doing planning, because so we have a paper soon to appear in TRO, which is very related to the work that came out of MIT, where there are all kinds of problems that I've brushed away in today's talk. How do you deal with asynchronous measurements? Everything in my world, in the world I described here today, assumes that that's just not a thing. What if you do want to give guarantees, which is a long-standing question, right? You can't just say, well, it's interesting, so I'll stop worrying about collisions. What if you actually want to deal with cluttered environments where the number of moving objects is substantially larger than like the ones I've shown you here, right? So there are all kinds of interesting situations where you have to deal with all kinds of interesting boundary conditions that weren't here. The other is, what if communication is actually not just asynchronous, but deeply flawed? In my case here today, it was perfect. So there are many settings in which there's room for planning. So we have some line of work that continues on that. And so yeah, there's lots of interesting things to do here in multi-robot systems. So I'll stop here and take questions.
So much. All right, we'll get started.
Just a quick question, like why limit it to like only 20 neurons? Are you using a microprocessor, or
yeah.
What kind of processing power do you have?
None, basically. This is a setting which is yeah. So this is my that's so.
I see. I guess my question is like
tiny little computer, yeah.
So like when you have only like 20 neurons, like a gradient optimization might become like a bit more harder. Like any thoughts on like using like direct search or like a evolutionary strategy to just?
Yeah, they may work better actually. They may work better. It's entirely possible that the reason why we are converging with such small networks is that we already have such a good model of the lower level parts of this problem in the form of the flight dynamics. And that's why this is proving to be okay. And it may not be for other problems. Because yeah, once things become so small, it's not super clear that you can get that much mileage out of gradient descent. But we observe good behavior, seems to work.
Thanks. Yep.
That's a good point.
Yeah, a quick question, we'll wait for more. Talking about end-to-end, right?
Yeah.
But in many of the demonstrations, you have direct state observations from Bicon? Like, is there any hope to add, like, pixels to action type of things?
Yeah, I'm less interested in pixels, but I'm more interested in getting away from the Bicon. So we are slowly getting rid of it.
What does it mean? Like, would you
For positioning.
With,
Yeah, I mean, like
still use like model-based stuff to get to positions.
Even if I have to have a camera and I do VIO looking down, and I have an IMU I integrate, and occasionally I have to learn to stop and use my compass to fix orientation, I'd be happier with that. So that's already getting away from, getting away from Vicon. We are close. We have some results in the latest ICRA paper that show that, but we're not fully there yet. So what we do is we actually use the Vicon every 1 in 10 or 1 in 20 measurements to get a fix.
In that case, do you have to simulate VIO, like, just to capture and learn the drift?
No. What we do is we just learn from corrupted position measurements in simulation. So no simulation of any of this other stuff. So we are very lightweight when it comes to those kinds of things. But yeah, that is one place where at least to be credible, you have to get rid of some of the sensing assumptions that we've made. When I gave this talk at another place, they said, this is charming, but your robots have entirely, they have the luxury of not actually having to do any perception. It's a fair criticism. It's a fair criticism. We have some other work on pixels too, torques, but not here.
Maybe a follow-up, like, about what to model. Like, so you say essentially the simulation is clever enough to capture all the relevant aspects, like, to transfer to the real problem. I imagine there are many things that you're not modeling in simulation, like, downwash from the propellers. You're not modeling, like, drag forces, like, for the propellers and so on.
Correct.
Are these coming out, like, the real transfer happens because you're randomizing enough in sim and you're kind of picking up on these things, or?
Yeah, both. A lot of the mileage comes because you randomize, and so the things do fly under each other, and what they see is a disturbance, right? And they see it often enough, so the system learns what are the right actions to generate when you get this kind of, they learn disturbance rejection, basically. Now, it doesn't mean that they will reliably fly. I mean, if you blast them with disturbances that they've never seen, you can destroy them or crash them and so on. But within that envelope, they learn pretty well. That was my first video of my grad student randomly kicking robots and so on and so forth. And they learn fairly large disturbance rejection, primarily through just interaction with each other, collisions, all kinds of incidental states they find themselves in. Yeah.
One more.
But they won't learn to avoid flying over each other to disturb each other.
No, they don't. They don't
right?
learn. They do not.
There's no idea.
There's no foresight. Correct. That's exactly right. And that's where, so that's exactly like the blind alley question, right? If there is, this is the thing that, I guess, I mean, that's why you have planning.
Well, if you had sensing.
If you had sensing and you could, yes, maybe, yeah. But you'd still have to, one of the things about these systems is, as you all know, is that they're inherently myopic. They make no prediction about the future, right? The actions are not, they implicitly make predictions, but they don't explicitly make predictions about the future. Yeah.
Just to follow up on that, well, I feel like they could avoid it in the same way that they avoid collisions. It would just have some loss term.
And you, in a way, get that already, right? You're already penalizing for being too near other robots. And so somehow implicitly, you're also penalizing for being in somebody's downwash. Not quite explicitly, because downwash only happens when you're stacked. Yeah. So,
new vectors.
Yeah. So,
Yep.
yeah. That's the other knock, by the way, is as you add more and more terms to that reward, people start to smile, and their smiles get bigger and bigger as you add more terms. So already, some of you, look, I mean, you write the physics of the vehicle, okay? You write a reward function that more or less clearly spells out what each term is supposed to do. Some may argue what is left, right? But I say that about control design all the time. I mean, you penalize for the things that you care about. So it's not entirely that nothing is left, but you have to hesitate before you add 50 more terms to the reward function. I mean, we are conscious that there's already quite a few terms there. I answered Nick's question wrong. That last term is the full 3x3 rotation matrix. It's not just yaw. I'll tell him when he comes back.
So I just had a question on the collision model. Suppose you were to get rid of that, would it still train, or does it get stuck in a local optima right at the beginning?
You don't get long flight episodes as a result of getting rid of the collision model. What you get are collisions that result in the robots ending up in states where they fall, and very often they land upside down on the floor, and the episode ends. And so if you want to give them a shot at flying to the goal within their battery life, the hope is that either they land the right side up and take off again, or they fly all the time. What you don't want is to have a episode-ending behavior. And so if you don't have a collision model, you see many more of those. And so then what ends up happening is you just end up with success rates that are much poorer. That's the real problem.
So it's sort of gradually giving it a good initialization to converge?
We don't do this in any real curriculum format, if that's what you're asking. Yeah. I can imagine doing it like that, but yeah.
So last question. You guys pass.
Thanks, Gaurav. I have a question for the collision dynamic avoidance, or it's not dynamic. Do you think it's good? So to model the collision, is it good for the recovering after collision in the real-world experiments?
You mean, would an explicit model help you recover from collisions better?
Yeah.
Our analysis suggested no, but the only one we tried was billiard ball physics. So we tried with some coefficients of restitution, and we tried with a completely inelastic collision. But the two collision models we have tried, and in fact, the performance is worse than the thing we do. We haven't tried anything else.
I see. Thanks.
All right, folks, we're already past time, so let's thank Gaurav again.
Thank you.